And I'm going to talk about Transformers XL. So excited for that. So I'm going to start. Okay. Take two. Hi everyone, I'm Florian. I'm a data scientist at BMO Capital Markets. And today I'm going to talk about Transformers XL. It's a new paper that came out recently from Cornell University with Google team. And they put a nice interesting twist on transformers. So the problem is that if you know what a transformer is, it's an attention-based, sequence-based model. And one key thing about transformers is that they have a fixed length, they have a fixed window size. And how people do it, especially the paper they always referenced themselves with here in the publication, is that they always, for the training, split up the corpus into fragments. And they say, okay, you want to train, you have only 100 positions, you just split up your text into 100 positions and then chunks, and then you train on this. But the problem is, if you do this, you kind of lose the context across those fragments. So the idea is, if you just split up a sentence in the middle, you learn on a sentence plus another sentence plus the half of another sentence, and then you move on to the next sentence, you're kind of removing the context from your training data. And if you are familiar with natural language processing, context is actually the core information you want to learn. You want to abstract from your corpus, from your text data. And here they propose, okay, we're going to fix this. We're going to allow recurrence in our attention model. So the take-home message here is, what is Transformer XL? Transformer XL is attention with recurrence. And they're going to show there are some challenges with it involved. And they're going to say, okay, these are the problems of the vanilla model, of the original proposed model for attention on large text corpus, and here's the solution they have and the challenges they had to overcome for that solution. And for just short recap, for those who don't know what's this kind of self-attention. So there was this paper 2 years ago called Attention is All You Need, which talks about multi-headed self-attention networks. So you have like multiple attention heads concatenated, and they allow you to capture different dependencies in your natural text corpus. And in a nutshell, an attention model or attention like unit takes a part of the sequence as an input. It applies self-attention on the sequence corpus, on each individual element, and get these kind of hidden attention embeddings. And then they do a feed-forward neural network to get the embeddings out. And this is just one attention node. And most neural networks, or most attention networks, they have like multiple of these attention nodes concatenated with each other, up to like 12 or 9 or 6. In the attention or you need paper, I think it was 6 and then again 6. And sometimes this kind of self-attention here has a mask. So the power of self-attention is that you can look, here is just 2 elements as input, but you can have multiple, like 100 tokens. And the attention looks how is the relationship across all these tokens, all pairwise combinations. And and in the special case, they have like they have a masked self-attention. And in the masked self-attention, information can only flow from left to right. So you kind of have only a left appending attention. And if, say, you want to apply this for your vanilla machine learning prediction for sequence text, this is what the network would look like. So you have your input at the t, like say you have a window size of 4. You have your 4 input tokens, and you have a masked self-attention, so the information can only move from left to right. And in the original conceptual idea is, the target is we just want to predict the next output. But for the training itself, they do a trick and they say, okay, for each position, you're going to predict the output for each position. And this is just a way of faster tuning the network. So in a nutshell, attention takes an input sequence. We have masked attention, so information can only go from t from left to right, and we predict the next token. And what happens if I do the sentence fragmentation for the training is I take a chunk, I train on this chunk, take the next chunk, train on this. And what is happening is that the error or information, there's no backward information across the different chunks. So ideally, in a recurrent neural network, you train on this chunk, you predict on this chunk, and then you have your error propagate through the different chunks. And so you can improve your network based on your performance on the next. And so as a consequence, information never flows across the segments. So I treat each segment as just individual problem, and I never reuse information I learned from the previous segment. And the other problem is that the largest possible dependency you can learn is limited by the window of your segment. So say I have only 100 position, I can only learn 100 position dependencies. But if I want to learn 101 or 100 or 200 dependencies, it doesn't work anymore. And as mentioned earlier, for the training, you have to split up your corpus into chunks. And you get this fragmentation, this context fragmentation.
Sorry, Florian, just to clarify, when you say chunks and segments, chunks of tokens.
Yeah, chunks. Yeah, segments or chunks of tokens. So I say I have a corpus of 1,000 words, and I have a window size of 100. What you can do for the training, you take 10 times 100, or you take 100 and then you always shift by 1, and then you get like an 89, right? Segments. Yes?
Does the token contain all the stop words as well?
Excuse
All
me?
the stop words?
Usually, yes.
The stop words inside your...
Yes. Usually in model language, you don't want to get a stop words because then the produced language is ungrammatical.
Okay, but you get rid of punctuations, right?
You don't have to, no.
You don't have to?
What, like if you want to read a text, for example, a summarizer, machine translation, you want the text to look natural, right? Yes, it will be easier if you get rid of some of the punctuations, but I think the text would be better quality if you keep them. And usually in deep learning, you do keep them for these tasks. Sorry to interrupt.
So, I just want to add something, then we do the question. So, for the older natural language processing models, it was very common to remove stop words, to remove like ing and verb, to put every verb to its place, every plural to singular, remove stop words, remove punctuations. But these models tend to either try to do embeddings on the word, pairs of words, so you don't want to have random noise in it, or they do like a bag of words approach, so you also don't want a random noise. But for these attention models, they're designed for sequence-to-sequence models. And they have an input from one language, and they want to translate to a different language, or they want to do something else. So they said, okay, we just use the raw data as it is. Yes?
So another question about using the raw data. If you are in a language like Chinese, you have characters, but characters form words. So in this case, we recommend actually do the process character by character in the character base, or do you combine it into words first?
I think.
Yeah, go ahead. I mean, you would, because these are words, right? If you go subword, then word embeddings are going to be like you have to go also with your representation. You have to go to the character level. But if it's words, you can still go from your Chinese logogram. I assume you're talking about traditional Chinese, not the simplified version. You can go from your logograms to embeddings, and that's perfectly fine. So Chinese isn't the problem, but like agglutinative languages and polysynthetic languages or languages towards that, like Turkish, they're a little bit more problematic with word embeddings. But yeah, but that's a comparative question. So let's hopefully keep that for the discussion points.
Yes. And what do they propose here in the transformer XL? So say for the first segment or for the current segment, I just do the self-attention as it is. And let's say, okay, I want to do a next segment. So what they do is for the next segment, we say this is the current segment and this is the previous segment. They treat it as a memory. And what they do is to concatenate the hidden states of the previous segment to the next segment. And if you that's it essentially. in a nutshell. We're going to talk a little bit more specific later about it, but just now for now. So all they do, they run it first, you get your hidden states, and then for the next segment, you run it again, and then for the hidden states you just concatenate the previous ones. And what's happening is that for each state, I always concatenate the previous state. See, add this, and this. And this in the training, they say, okay, most of the time, the memory is the sequence length. So we always have the segment and then the previous segment, the two pairwise. Yes?
Why it wasn't used before?
I don't know.
That's a good discussion point. We'll get to that.
So they're concatenating the output of the hidden state from the previous tokens into.
It's hard. Let me go to the previous slide. So for this, they concatenate this one. For this one, they concatenate this one. For this one, they concatenate this one. So it's always shifted by one. And later I'm gonna show you why this is important. Yes?
You mentioned that it's normally the length of the sequence. Does it have to be? Is that a condition in this?
No, it doesn't have to be. They do it because of performance reasons. Because you want to recycle your previous hidden states. So for the training, they say we go back one sequence from our predictor sequence and we just recycle the hidden states from our previous step. And that's why you can train faster. But in pure theory, you don't have to do it. Any other questions? So let's go after the model is trained and you want to predict a new position. So in the vanilla step, what they do is you start at your first sequence and you predict the next token, and then you move on. You shift by one and you do it again, and shift by one, do it again, shift by one, do it again, shift by one, do it again. And what's the problem is that you can only consume one segment at a time, and you only do one prediction. So this is very expensive and it's rather slow. And because you shift only by one, you kind of relieve a little bit the context fragmentation, because you see every position. Now you see every position. So for this vanilla prediction is also very common, like for if you predict with the recurrent neural network or some other model. So, any questions for this? Okay. So let's see. So for this new proposed architecture, as you see, for this position, you would use this context. And then for this position, you would do this context. And then for this position, you would do this context. So if you want to predict this data point, you go through here, and you have from x3 to x12 the data to do the prediction. And this is why you see why it's always shifted. Like this goes here, and this makes sure that for each segment, the dependencies shift by one. And this is very important because of this, your memory and your runtime grows linearly in respect to the number of memory you use.
Can you explain that one more time?
So if you do it the other way around. So let's say you want to predict this position, right? So which data points are used? So you use this one from the current sequence and these three from the memory. And then for each of these four which you used, this one was used these four, and for this one was used these four, and for this one was used these four, and for this one was used these four. So essentially, these are dependent on the memory from the previous one. And these hidden states, you just store it from previous run. So essentially, you run it here, you run it again, and then this hidden state already took information from this state. And then you run it again, and you consume the hidden state from here, which has dependencies or information from this hidden state. In this way, even though you only run segment by segment, this state still can take information from multiple segments away. So for each, what they say, depending on how many layers deep you go, the dependency shrink by 1 layer. So if you say I have 4 layers, I go back up to 3 segments. And here I have 3 layers, I go up back to 2 segments.
So they're saying the information would propagate more so than without this recurrence that we're seeing. And just it might be obvious, but each of those sort of dots are an embedding vector, right?
Each of these dots is like the Z state from the attention. So you run attention layer, here would be the attention layer, and you get your Z states for each data point.
You talk about the memory growing linearly as you increase the context length, increase the number of segments you processed. Looking at this example, it looks very lower right triangular. Based on the segment rat, there are going to be some states in the upper left of this diagram that are no longer relevant to future predictions. Are those still stored in their implementation?
So I was looking at the PyTorch code, and the way they coded it, it seems that they just store the whole output. So they just store the output from this neuron, from this attention kind of unit, they just store the whole output. So it's an array of matrices, and they just always store the whole matrix. Yes?
My understanding is that it's like calculating the information and compress it for each segment so that you get all the information from previous lines and previous segments, right?
Yeah.
So for example, if we have changed in the, for example, topics to paragraphs, how we can show that, okay, the previous informations aren't noisy, they're relevant to things that we predict now. So how do you tackle the noises?
So later they say they have a position-wise embedding. So they make sure that if something is very far away, it's going to have very low weight.
Also, they will wait.
Yes, they have a position-wise weighting later. So
We'll get
later we'll talk about this. So this is what it would look like, the triangular maxes, for essentially for the last data point. Yes?
I guess my question is, that is when you are evaluating, the triangle is going to be like that and exactly shifted 1 by 1. The chunk doesn't mean anything when you are doing evaluation, right?
I think if you do it 1 by 1, it would shift by 1 by 1 the triangle. But this is what I think was not very clear in the paper, how they do it. Because they also do the prediction later, they showed they do it chunk by chunk. And what they attend is always the whole memory in the PyTorch code. So for me it wasn't very clear. So we were still talking about this.
I'm also very curious about, because I have the same confusion.
Yeah.
Because if you do shifting exactly by 1, the way you used to evaluate your earlier nodes are not going to be the same, so you cannot store this and pretend that they are going to be the same. So they must be doing something chunk by chunk in order to recycle all their own.
Yes. So here they show they're going to do it chunk by chunk. But still they say they have this kind of triangular relationship, right? But in the code itself, in the PyTorch code, when I looked into it, the memory is always the whole memory attached to it. So from my intuition, it shouldn't be like triangular, it should be just the chunks you use. Are there any questions about this? This is like the core component of the model.
A question from online, but the online has probably 1 or 2 minute delay. So the question is this what the authors refer to as shifting downwards per segment?
Yes.
Okay.
It could be also that their implementation is a little bit older than the final version of the paper. Just saying.
Yeah, okay.
It could be.
I think it's just not clear. Later we will look at a bit of the attention layers visualized, and there it seems it's actually like this. But I wasn't very clear to me. And I've talked with you about it, and there's also questions in the audience, so it seems not to be very clear in general. So a lot of people have that issue. So there are any other questions? Feel free to ask. If not, just move on. So this is kind of like a pseudocode, kind of pseudo formula of how they do it. And essentially they say, okay, from the previous layer, the next segment, so this is the output. So we want to predict this n layer. And then what they say, they have this h tilde from which is kind of the hidden state plus the memory. So they say we have the previous segment, the hidden state from it, and they say we do a stop gradient. Stop gradient just means we don't do any backpropagation anymore beyond these things. We don't care about these anymore. And then we say, okay, we have the +1 from the current segment from the previous layer. And then they just do the attention. So this is just, they do the query key value vectors. So it's basically, I have the matrices, the key value and query matrices, and for attention, essentially, it just makes a query from query times the key, and then gets a value associated to it. And one thing you should pay attention to, so this is a D times L matrix. So the query is always the segment, so it's size of L. Whereas this, with the tilde, it's like 2 times L, because I have the previous segment as well. So it's a D 2 times L. And then they apply the self-attention on these matrices.
Or can you just define D and L for us?
So L is the sequence length, and D is the hidden number of hidden dimensions. And 2 times L is twice the sequence length.
Because they concatenate them in the length dimension.
Yeah.
Those
Yeah.
ones, 2L.
So they get concatenated in the length dimension, exactly, Tara.
And if you want to know more about the vanilla transformer networks, we have a video on our YouTube channel about it, details.
I know.
And they take it another step further, because you don't necessarily have to do L in the evaluation step. So they say instead of L, here using only L, so 2 times L, they say we use M. M is like they say it should be a multiple of L. So in the evaluation step or in the prediction step, they say during training M is like the sequence length, and then in the evaluation M is a multiple of the sequence length. And it's a multiple of sequence lengths because they do the prediction segment by segment. And it has to be a multiple of L because they want to recycle those hidden states.
Could you reiterate that point again?
So M is like the memory, which is what before we showed was the previous segment. And in the training phase, they set M to L, to the sequence length. So essentially here it would be 2 times L. But now they say in evaluation, L can be a multiple from, M can be a multiple of L, like 3 times L, or 4 times L, or 5 times L. That means I use the previous 5 segments, or the previous 7 segments, or the previous 10 segments. And then these matrices will be L plus M, and not 2 times L.
So when you say evaluation, you're talking about inference.
Yeah, inference or prediction. Are there any questions?
So is that supposed to speed up the prediction? Or just give more context?
So it's a way of giving more context while by keeping the speed, right? So you can say, okay, do M whatever number, but then you cannot recycle your hidden states anymore. So you go segment by segment, and then you can just store the memory of the last 10 segments, right? But if you say I want to do last 10 segments plus 4, you somehow need to calculate these 4 steps, right? And you would lose money. The idea here, time or energy. The idea here is just to recycle the previous iteration steps. So most of the tricks they do it because of efficiency. And they themselves said, okay, if you have infinite memory and infinite computational time, then you can just do a attention layer that's the whole sequence length. You don't care, right? Mm-hmm. You can do whatever, but it's not feasible. And the idea here is, the core ideas or the tricks they do is, we want to introduce recurrence, but we still want to maintain some speed. So I think it's later one of the discussion points is, or recurrent neural networks are a bit slower because you can only, when you train, you always need the previous hidden state. And you cannot batch things up very easily. And the power of self-attention was that you use only a fixed sequence length. And then you can make all your segments, and then you parallelize it on your graphic card or in your tensor processing unit. And later the conversion and discussion points is the question, do we still have this kind of bonus or this kind of parallelizability for this architecture? Yes?
I don't know if this is different for images and text, but from when I've used recurrent neural nets, the whole point in training was to learn the world of what you're trying to learn. So in this case, the world of words, right? And then during testing, it's already learned this environment, so it should be able to recreate stuff. So why do you need so much context during test time?
So in general, there are long-distance dependencies, right, that vanilla RNNs or even LSTMs would miss on, right? So you may use the pronoun he referring to a person that you talked about like 2 paragraphs ago, well, or a paragraph ago, right?
Yeah.
And that's just too much to expect for an LSTM, even with gates to remember. And the idea of self-attention was to keep that sort of context, if needed, all the time. But the problem with it is that because it's the size is fixed and usually not that big, even them they're gonna miss so some of that relevance. And the idea of this paper is to connect with bringing back the recurrence so that it could sort of keep the long distance dependencies there.
I think the way I like to think about it is, imagine you read a thesis or a long document or a report, and there's some acronym described at the very beginning, the first page. This acronym is still used 10 pages or 20 pages down. But if your attention or your recurrent neural network will not know what the acronym means later on. Of course, whatever, if you do embeddings, it will not affect it, but it's kind of the idea. And I think most of the times when recurrent neural networks are used for images, you kind of try to learn, oh, these are hot regions or these are cold regions I'm interested, these are regions not interested. And these regions have like some kind of spatial limitations. And it's kind of what it should optimize to is to identify the border between my region I'm interested in the region I'm not interested. And normally, if you do your window or your frame for the recurrence, it should be able to capture this information. And it doesn't really matter for your image if your information is like here, what happens up over in the upper left corner.
Question for my line.
Yeah.
M in the slide, I think it is fixed during training and increased during evaluation. How do they do this and why?
So it's fixed during training because they use this kind of pushing down segmentation, segment by segment, and they want to just concatenate the memory. And it's increased during evaluation because they want to capture longer dependencies. And because they can do it. Right?
And how implementationally, how would that work in inference?
And they
Having-
cache them. They, have
They
them
just cache
available.
it, right?
Yeah.
So
That was
the-
the question, sorry.
Oh, okay.
Sorry. Yeah. They
So
cache.
because they cache, they have access to that, and
Yeah.
they can use whatever context that they want there to be cached.
Yes. And they train and optimize the network for segment by segment. And when it's cached, they can only attach segments, or they only want to attach segments. When I was looking at the things, there's nothing preventing you to punch in end to end whatever you want, even after the training.
As long as you have computation.
Yeah. But then you no longer can take advantage of the architecture. So later they say they're 1,800% faster than recurrent neural network. And the reason for that is because of this kind of caching of the previous hidden states. Any questions? Yes?
So if I push M beyond the light cone, dimension, it goes so far into the past. In the inference stage, am I still getting new information, or the only information I see is given by that light cone even?
The light cone Yeah, I say yes, it would go. The light cone depends on your M, right? So if you make your M bigger, your light cone will become bigger. So the light cone was like this because the light M was 4.
I see.
Yes?
Sorry, but the light cone depends on your training, right? Because you never train a wave that costs.
In the training, your light cone is your sequence length. But in the evaluation, your light cone can be bigger.
But then the light cone will have to go through a path that has never been trained. How does that?
No, because the matrix is it's a good question.
That was my question.
So maybe we can talk about this later in the discussion part. So
I think it comes from the reduction step that's happening during the self-attention phase.
Yeah.
It's not important, or not particularly important, which position it falls at, partly because of the position embeddings we're about to talk about.
Yeah, let's touch back on that point in the
Yeah.
discussion.
yeah, this was also
Seems to
the
be.
we were talking about this before giving the presentation as well. Yes.
This is a question for you. So what's so peculiar about this reduction phase?
It's nothing peculiar. It happens in any standard attention model. It's just a method of reducing a variable length context down to something fixed length that we know how to deal with in the equations you saw and then future steps. There's nothing special about it.
You are talking about training phase?
Well, during the training phase, you're reducing from a vector length m down to, for each one of those hidden states, a single representation. At inference time, you can multiply the length of the context you're providing it. The reduction step is still going to reduce it down to a representation of the same fixed length.
Okay, so it's not the reduction in the sense of all reduced.
It's not a complete reduction. It's the same reduction that any attention step does.
I mean, it's not related to distributed computing.
No.
Oh.
It's not map reduced.
It's not map reduced. So if you remember, there's a positional encoding for the self-attention network, where I give a position embedding on top of for each position depending on the position in the sequence. And the problem here is now I have 2 segments but only one position embedding. So what's going to happen? I'm going to repeat the position embeddings, and these positions embeddings become non-unique. So now we have 2 different positions who have the same position embeddings. And they were wondering, so essentially F is like the attention, and you have the previous segment which we use and the current segment, and you see this attention embedding stays the same, and that's the problem. So they were thinking, okay, what can we do to change this? And I said, okay, let's do some relative position-wise embeddings. So no longer on the absolute position in your sequence, your embedding depends, if you query 2 positions later, it just depends on the relative distance of these 2 positions. So you have to think of it. You have your query, which is your length L you want to predict. And then you have your L plus M memory, which is your key. And then you do the attention on this. And for this L plus M, it's just the difference in length, like the RAE, the position, relative position, is basically the number of positions between this position L query I'm querying and this M or memory position I'm asking for. How they do it, they change a little bit the attention hat, how it works. And it's not very straightforward explained. So this is what the traditional attention looks like. So we have this query and this key value. And this is kind of a normalizing step, and then do softmax and then multiply it with the value matrix. And then you get your self-attention for that given input. And they say, okay, we're going to this query times key, we're going to extend it with several parameters. And one is like kind of like a content weight. So it's the original score. It's just the query times key. Then they say, okay, we add a positional bias. So in respect of the current content. And it's just a sinusoidal function. And instead of taking the absolute distance or the absolute positions, it just takes the relative distance between the query and the key. So they just extend it. And then it extended for another term, which is kind of like a learned global content bias. So it's kind of independent from, a little bit independent from the current key and value. And then there is, say, they learn a global position bias. Yes?
So it might be related to the same question, but I just don't understand why the position encoding is even needed in the first place, because presumably those two chunks that they go in the same position in different places, they go through the final answer through different links, and the links have different values. Why aren't those weights on the link enough to differentiate their contribution? Why do you need to supply another positional encoding?
So there is. So usually, when you want to generate natural language, you need some reference as to the order of the words, right? Where would you?
So what I would say is this layer and this layer is the same layer. This is from my previous. So now it sees the same position and it sees the previous position, right? So when I run it through, it kind of doesn't really abstract well on it. This is what I would say my takeaway. Because these hidden states were just created previously, and I just treat them as a constant and concatenate it. Or what do you think?
I mean, I'd say it's not a pure recurrent network, right? So it's not like you do one step and then you go next step and then you go next step. You're sort of running this in parallel. You need to keep that sort of sequential information somehow. You need to know what happened before what, right?
But the weights are structured in a icon that knows that. Who's at the edge of icon, who's closer to that icon. So
I mean,
for example, the x1 position, if I want to predict the final one, upright, right? x1 and x6 may have the same location label, but they are going to propagate to the final output through different value of weights. And we're going to train on those weights so we know the difference.
so you're saying because there are weights and I can see them, the network should also understand them. But that's too much to ask from the network, right? If it was recurrent, again, more, because at each step, you know which is closest, you sort of have that notion. Again, there you miss a lot of information. And I know, and I know the point, and I wish it worked, but usually you need some, especially with such a heavily parallelizable architecture, I'd say you need some positional encoding. But that's very interesting. Like I wish to see if they tried it without, and see what happens. But I would claim that they have tried it in the first one and they failed miserably, and that's why it's there. That's my guess.
I think later they do a study where they have all or they have it with all the position, relative position wise, and it works worse. They've done it, yeah.
With or without?
Without and with.
Oh, okay. Then that would sort
Yeah.
of be a proof to his point. Okay, yeah, great.
So there are any questions on this? So this is what it looks like in the final version with all the formulas written out. It's a bit intimidating, but we're going to go through there step by step. This on a high level. So they say this is the content-based metrics or the content-based attention. And you see it's with the text, the memory and the current sequence into account. And then they say there's a location-based. So as you can see, this location-based only interacts with the query, right? And so it's not really taking the memory into account. It's just a pure location. And this Ri minus j. So this is essentially the attention of layer n for the segment tau between query I and key j. And when I do the attention, you have all your I keys queried against all your Y keys. All your I queries against all your J keys. And the relative position is the synthesizer function which takes as input this I minus j. And this is a trainable vector which they use for the global content bias. So you see it goes through the whole memory, and And then I have one for the global position bias, which just takes the location bias and the suicidal function. And once this metric is created, then apply the softmax, just as the other multi-headed attention, and then multiply it with the value, and then do the layer norm and the position-wise feed forward. So there are any questions? It's a bit much to digest, I would say. Then let's move on to results. So
that's... Yeah, we'll just take a short 5-minute break. So feel free to just get up, stretch your legs, have some more food, and then we'll start back after that. Thanks, Florian.
Okay, let's move on. So they ran their model in different experiments, like Wikitext and Text8 and some other, which basically the goal is just predict the next token, if I understand correctly. And the way they evaluate is using perplexity. So they didn't do like accuracy or whatever one score, but the perplexity which kind of measures the entropy of an expectation. So the higher your perplexity, the lower your perplexity, the better. Exactly. And as I said, they can have different length in the training and in the test or in the evaluation. So here they use 384 in the training and 1600 in the test. And they have 103 million tokens across 28,000 articles with 3,600 tokens per article. And as it's surprisingly, their model did the best compared to all other models in the category they chose to measure their models. It's a very surprising result. I wouldn't have expected to see something like this in a publication. And later we have also a discussion point about this, so we can save it for later. And then they look at NVICI 8 and get similar results. And Text 8 is a very similar challenges. For these two, they used a little bit bigger network. And then they have an ablation study where they justify these kind of changes they did. And before there was the question if the positional embeddings make it better or worse. Just to clarify, the positional embedding makes the model better, not worse. So the positional embeddings makes it better. And the way they do it is, so they say we have here recurrence and we have the encoding, and ours is their encoding, and these Shaw et al. Vashni and Al-Rafou, like Vashni and Al-Rafou don't use the vanilla encoding, and Shaw et al. They just use a little bit of changed encoding, because they say in the paper our encoding has 4 components, A, B, C, D, and C and D component has the positional encoding, whereas this Shaw et al. They have the C, D encoding missing. They only have the A and B encoding, so they don't have the positional embeddings. And they say, okay, our model performs better than all of these. So they say, okay, our positional embeddings make sense and our recurrence makes sense.
What does the loss feel
after? I'm not sure. No.
Sorry, what's the question?
What's the loss again? They say half and full. It was something with the sequence, but I forgot what it was. I don't know.
I remember seeing something.
If anyone knows the answer, feel free
Yeah,
to
if you
speak
find
out.
it, we'll say. I don't remember either.
But we can carry on.
We can just carry on. Okay. So, in conclusion, so this here, the Transform XL can enable language modeling with positional-based architecture, recurrent architecture, and can have context beyond the fixed length. And they say they can have longer dependencies, 80% more than a recurrent neural network, 450% more than a vanilla transformer. And because of this reuse of the previous memory state, they say they are 1800 times faster than a vanilla transformer on their way of measuring it.
Times.
Times, yeah, times, not percentage. So they say times, so it's good, right? Nothing I would complain about. And we can now look at a few of these attention layers to understand what they're doing. Sometimes they're really rather easy, sometimes they're more difficult. Here I think in this card is a bit more harder. And what they did the Wikitext 103, and you remember they had 1600, so they have 16 10-head transformer layers, so they have a total of 650 attention positions. And then they say, okay, this is like the average across all layers, across all positions in the Wikitext. And what we see is, the attention tends to be bigger on the more closer, on the more nearby tokens. But there's no big trend to see here. And then they say, okay, we look at layer 1 and the first layer at height 8, and they see kind of like a uniform attention distribution. And the idea is, oh, you're in one of your first layers, so you don't want to have strong biases, you don't want to remove certain random positions. So they say we have kind of, you kind of screen the entire memory span. And the focus for certain sections happens later.
So just want to add the answer to the question, full and half. So they're applying cross entropy to half or the full segment of yeah, from the loss.
Okay. And say go to layer 8. So we have 10 layers. So head 78. And then we see it becomes considerably more sparse. And we have certain position where the network focuses on. And it kind of says, okay, we screen the initial whole memory, and then as the layer progresses, we identify the sequences that are important for me, and then we just go into this kind of memory position. And in the last layer, we see it looks a little bit like the first layer, but we see some more stronger patterns here. And what they say, each target location kind of has its own focus. So they say, okay, you're this position, after all these layers, these are the possible keys that are relevant to you. So essentially for each position, depending from where you land, from all the previous landers, it shows you like the keys. So this is
This was the 5 minutes.
just enjoy another 5 minutes break.
That's
We can move
Can
directly to it.
is it? Oh, okay. Sorry.
So-
Go on.
There's going to be some discussion points from the facilitators, but they also came up here within during the presentation. So one thing was now we use the hidden states from the previous segment, right? So we lose the power of the attention network where I can completely split up the network. So I always have the memory from the previous sentence. Can we still use the fast and parallel training? And I think you can still use it, now that I was thinking about it. Because for the recurrent neural network, you always have it from all the previous positions. But here you always shift by 1. So if you have 10 layers, it always shifts by 1. You just need to save the last 9. So if you say I want to predict this position, just give me the last 9, or let's say the last 18, because I also want to have the full memory for the first one that's relevant, right? And then just give me the last 18 and then run through, and then give you the prediction. So you can still parallelize it, but you will need more memory. You just need to give it enough previous sequence so it has the fully built memory. That's the way I think it. Feel free to disagree.
Do you remember what's the M that they use for evaluation? In the book?
One was 3,600 and one was 7,000, I think. And the one was 1,600 and one was 3,000. Wait a minute.
So I'm just wondering if you're going,
So
Only-
3,200 for one and 1,600 for the other one.
if you're going that many steps back
Yeah.
and reuse your hidden states, why not just use an attention vector that includes all of those segments? You know, why not increase the segment length by that much?
Because if you would use an attention layer for the whole sequence, you have to calculate the attention for everything. But they just want to recycle it, right? Because you think they go through it.
Yeah.
Guess that the matrices become smaller? I don't know.
So
It's a
there's
good question.
trade-off,
It's a good
right?
question, yes.
There's a trade-off.
There's kind of a trade-off, I would assume.
Yeah.
Then, so at the very beginning, I showed you the slide for the vanilla transformer. So in the vanilla version, they used perplexity, so kind of a perplexity additional loss between the layers. And the question came up, why not use it here? And I think it's a good question. And I also don't see any reasons why not to use it. I guess they just didn't want to, or it didn't occur to them, or they don't see it necessary. But I think there would be no reason not to include it. Maybe they had it in, and they take it out, and they see there's no difference with or without, so they just took it out. But I don't know. Oh, this was the auxiliary loss, sorry, not the perplexity, it was the auxiliary loss. So if you see, for all the comparison, because all the different models, they use perplexity, which is kind of the entropy of the next position. And the question was, this perplexity is not a really strong indicator if your model is actually better or worse than the other models. And normally what you should do is perform a real world task. And so the suggestion was like, they should just run it. It was also, when they submitted a paper, one of the comments was, oh, you should compare your performance with like BERT performance on certain challenges as with BERT. And I agree with this comment. Like, if you make it really comparable, you should use first a real world problem and then show how well it works and compare it. But it's something they can do.
So back in the day where everything was these little modules, so like in speech recognition you had your language model, and the acoustic model, and then you had your morphological dictionary. It made sense for each one to be, tested individually as well. Right now, a lot of things are end-to-end. But it's still a good measure for the language. Like it means that your language model is predicting better the next word. That's for sure. But I think your point is more towards, but does it actually work better in applications or in end-to-end when you're using transformer network for bigger tasks as opposed to just predicting the next word?
Yeah, so this is really where my concerns were about the paper. So for example, when they're doing the comparison on Penn Tree Bank, they're comparing their model to, I think, general models that are fine-tuned. So to compare to BERT, I mean, BERT trains on one corpus over here and then performs well at a task over here. Whereas this is showing that, I mean, every model for every one of their benchmarks is a completely different model. So different number of parameters that they've tuned. And so what they've shown is that their model can compress some, 100 megabyte examples of text very well. But what else?
So BERT was the sort of towards the representation, then therefore, and from there you can transfer, learn, and do a lot of other tasks, and that's why they had, because that was the sort of, otherwise it's just transformer network, right? So to show that you can actually use that resulting embeddings to do other tasks, then like BERT came out. I still think it's fair to, if you want to compare language models, it's fair to use Perplexity.
You're training your test set are the same when you use Perplexity, and that's really the fundamental problem.
So not necessarily. So you can test
in this
it.
paper.
I see. You can test your Perplexity. Yeah. You would test your Perplexity on what you trained, right?
Yeah, and just to add to this discussion, I think they're just doing intrinsic evaluation, and it doesn't mean it's going to do well on downstream tasks. And I think someone can take the idea, just get the same sort of representations that BERT is focused on from this model and try it. And I think the discussion point here, it would be interesting to discuss what sort of tasks do we expect this to do better on, based on the ideas they incorporated.
So it took a year until BERT came out of transformer networks, right? So I think it's fair to let them also do all those experiments, because it does take a while to transfer.
OpenAI just had their next one after their first big transformer fine-tuning just came out last week. Yep. And it's so good that they are scared to release the model.
So that one we're talking in how many days?
2 weeks from today.
2 weeks from today.
I wish I could be there.
Early March.
Well, we also live stream, so you're welcome to join on that. Yeah.
A question from online. So the question is actually, can we adapt this for images as input, like say videos?
So one of the reviewers asked exactly the same question. They said they don't show, can you use this for non-text data, let's say audio, video, images. And the way I see it right now, I don't think you can, right? I don't know. Well,
So
Why not?
yeah, well, I don't see any reason not to. So like, because if it's sequential data, and so for language, like if it's sequential data, long distance dependency matters, absolutely go for it.
Yeah.
If you have short sequences, you don't have long distance dependencies, then don't go for it.
I think there's a paper called Image Transformer, right? I came across, but I haven't read it.
I think my concern was just a little bit about the embedding. So say you have an image, you have like 3 measurements, right, per data point. And what they expect as an input is considerably longer. Base embedding, and then they add the positional embedding on top of it. But, so this is a little bit my concern, but again, as you pointed out, they use image transformers. So there's a good chance it might work.
For images, it's a little bit more tricky because image has, it's not only sequential, it has arguably more degrees of freedom.
Yeah, I think if it's...
And they have their own attention, which is a little bit different from self-attention.
Another question, with their segment level recurrence, they mention that they cache sequence of hidden states. Is it possible to get the same outcome with GRU or LSTM and cache the hidden states?
So you just do the same thing for LSTMs?
Why do they want to do that?
So, I think caching, and correct me if I'm wrong, I think caching here makes sense because you're parallelizing your computation, right? So you keep that, it's still going to get computed. In LSTM, it's step by step. So even if you cache it, technically we do cache also. So for a few tasks, you have these context vectors that your encoders run, and you're at decoding time. The decoder has access to all the time steps of your encoder, and the attention layer will then tell you. So I think technically we do cache, but in that sense, I'm not sure if that entirely makes sense in the sense that we just saw. But in the sense of context vectors, we do cache. So decoders usually do have access to all the encoder's time steps.
Sorry, I think in this case, the caching is related to their difference. The transformer, in transformer, the weight sharing is on the same layer. In RN, the weight sharing is on different layer. You use the result of, you use the output of the previous time step. You feed the result into a network with a shared weight. That makes it, you know, in this case, the caching doesn't really make sense.
No. So, are you saying it doesn't make sense because in RNNs, actually in RNNs it's from the same layer. In here it is from the previous layer, the one layer down, right? It's the other way around.
Yes. Exactly. So if you unfurl an RNN, it actually looks like, you know, this weight is identical to this weight is identical to this weight.
Yeah.
So, if you cache the any weight in the middle, it doesn't mean it can be used to immediately to process the if you just shift this sentence for one word, because for the next word the layer the weight sharing is like, these are identical, but these are not identical.
So you're saying it doesn't have direct access to the encodings, rather it propagates through the layers. Yes, that's a good distinction. Yeah.
Yes?
Do we know the theoretical minimum perplexity of like this task that they're evaluating themselves on?
0. Theoretical would be 0. Your empirical distribution should be the same as your predicted distribution, right?
Because this is training data? Like, so was the evaluation on unseen data, or was it?
So it is, and I need to refresh my memory on this, but
It is ordinary. It is customary to test perplexity on the training data. That's perfectly fine because you're still trying to predict your the perplexity of a really big corpus, right? It's not like the train and test. So it's not the bias variance. It's the same sort of that you see in machine learning. Because it's unfair to expect the machine to predict the next word on a corpus that has just talks about the
OpenAI did it, so they have better perplexity on some of the same texts that they used for
yes,
this
and
paper.
we get to that
On a completely different corpus.
Yeah, we get to that in 2 weeks. But just saying that this is how it's been done in the past decade.
With similar numbers of parameters, by the way.
Are you from Open? I'm kidding.
It's,
Do you remember how different?
How do you measure
very,
that?
very close.
If you test and train it.
So for perplexity, I mean, just we need to remember it's perplexity. It's not accuracy. It's not. It's a measure of being able to predict the next word. It's not like so when you're predicting the next word, it's not like you know the exact tests like training set. Like that next word can occur with a lot of different other combinations, right? I can say hello, and then I can say how are you? I can say hello, and then I can say. I'm not doing well today. So like these combinations. So it's not the same as you see in other machine learning supervised tasks.
But you cannot get perplexity 0, right? Because the next word can be ambiguous, even the same previous words, right? It's possible to have
theoretically, yes.
Yeah. So there's some minimum non-zero.
Yeah,
that
true.
they
Well,
In
no,
practice.
in this regime, you're
Yeah.
training and testing on the same set, so the minimum theoretical perplexity really is 0 because the network has seen the entire text.
You're saying it could memorize
That's
the entire
right.
text. Okay.
And with hundreds and hundreds of millions of parameters, I'm surprised it didn't.
Any other questions?
Oh, wait, this network has enough parameters to, in theory, memorize the entire training data?
There was a couple of hundred million, right?
Yeah, 360 billion parameters.
Okay.
Well, some of the data sets are 100 megs in size, so do the math. I don't know. Well, close, not too far.
I was curious about the visualizations you showed at the end. Did they show how it adapted during training? So whether it changed during training?
No, they just showed
So-
it at the end. They showed the trained model and average over everything. Like the first one is average of everything, and the other one is the average of all. Like they run it to the whole corpus, and then say for layer 1 had 8, they should take the average over the whole corpus for this layer on this head, and so on. But they don't show. Well, I assume these are just random weights at the beginning, so there must something happen.
So just to clarify on that point, so data sets, and sorry, I didn't mean to be dismissive of your points, just my memory is involved elsewhere. So usually it's not fair to say, oh, the corpus is that big. For natural language, it's not, because your complexity grows exponentially with your sequence as well as with your vocabulary size. So we're talking V times length of your sequence, right?
Yeah,
So
that's-
if you're doing the
that's
calculation,
good, yeah.
factor that in. Like perplexity, like, and those scores that you see going to perplexities, like from 20 to, I don't know, 18, that's pretty good. Like it's not, we shouldn't discount that.
Yeah, but if you look at the size of the sequence that it's looking at in training, so this is what, 380 characters or something, right? And so you're really cutting that search space down because now you're talking about
It's the other way around. No,
380
that's usually the misconception.
380 grams and
It's the other way around. That's usually the misconception. The longer your sequence is, the harder it is usually to predict. Like because you're thinking of the next word. What's happening in sequence encoding is all the different combinations that can happen.
Yeah, the space is growing.
The space is crazy big.
oh, of course, because it's language, it's combinatorial explosion, but I'm saying that suppose there's a series of characters that only appear once in the text, and it's a unique marker, then it can encode everything that follows that up to the size of the input attention space as something to be memorized. So it can greedily find unique character strings and use that width. So I agree with you. I'm pointing out that, so I, in my notes, asked, why did they pick these numbers? And what does the fact that different corpuses have different, first of all, they all have different training, testing, attention size, right? They train on this size, test on this size, and then they change those hyperparameters across the different corpuses that they're giving their benchmarks for. I find this highly suspicious. So like they're playing somewhere in their lab before they publish the paper, they're tuning on, okay, we're going to train with this width, we're going to test on this width, and we're going to change that across whether we're doing, the only time they kept it the same, I think, is between NWiki and Wiki or TextAid or whatever, because, yeah.
Right, so are you talking about the M, is that?
Yeah, I'm talking about the size of the attention. Or sorry, the size of their memory.
I mean, it's a hyperparameter, right?
It is a hyperparameter.
I mean, I know you like GP2 better, but it's I mean, you can, I mean, it's just like, obviously, you need to change your parameter size when you go from one task to the other, or from one corpus to the other. Like, I mean, yes, it would be great if you don't, but in practice, I think you do. All right, anyhow, let's move on. We can take it offline.
A question from online. Why no grad is used with the previous hidden state?
Because they're just treated as a constant memory input. You don't propagate the gradient to the previous state and on and on and on, right? If you would do the back propagation on the memory, you would back propagate it through all the sequence back, but they just stop. They just only do the error on the current one. This is the way I understood it.
And the weights responsible for generating those previous hidden state was already actually being updated at the current state. So it only determines the
Yes. Yes.
So whenever I see like hard limits to like say for in here the contact size, like I keep wondering to myself, is there a way to not have a hard limit and instead like make that like the attention length manage that organically, so like for example, keeping the more important information and maybe like sliding out the less important ones or something like that. That seems to me intuitively like more similar to how a human might do it. So I'm just wondering if people have thoughts on that.
So I think that's what attention itself is trying to compute, right? What are the important parts and what are not the important parts? So I think in this particular case, I'm not sure if it is possible.
You can think of the attention as the max. So certainly people have a maximum. We can remember 7 things plus or minus 2 at a given time, but it doesn't mean we always remember 7 things. So like you said, attention is trying to say, here's the most things you could look at with your attention, and then if you have 0 attention values, if your Zs are 0 for some of the stuff, you ignore it. And so it's just the max.
Like there seems, for people at least, there seems to be a difference between like the attention and the working memory. Like attention is like what we're focusing on at the moment, but at the same time, like in our working memory, there could be a much larger chunk that we're trying to like relate to, whatever we're paying attention to at the moment.
And we're not perfect either, right? So a lot of times we go back and check, and like if you're summarizing, you go, it's a big, for example, text, you go back and check.
Right.
But you remember something, so
Yeah.
in that case, yeah.
Because like a lot of times when I'm say like reading a newspaper article, like I'll find myself looking at somebody's last name and realizing that like this person must have been introduced somewhere like way earlier in the article, but I don't remember anymore and have to go back and look. But then if they're limiting to the attention to like 300 odd characters, like that seems to probably like
The only
not
time
really enough to like for like say when I'm reading a newspaper.
So one of the time I saw something similar what you're proposing is, I saw someone say, okay, make a UGAN. So UGAN It has the big image compressed small and compressed back and then across the U. And then they suggested we make a U GAN with attention. And then they had the attention between each GAN step, and then they suggested another global attention, where you can feed always to the global attention from every layer. So I saw some people trying this, but I don't know. Have you ever saw global attention for a sequence model?
So that local attention, is it dynamic?
No, the local is always from kind of between the layers, right? Or between. I forgot the detail. I just remember they had two types of attention in the UGAN network. One was a global and one was a local one.
I mean, I remember hearing or reading this, but I don't remember the details of it.
Is this too much? Like attention was so big that you can think any neural network architecture and add attention, there's already a paper on it.
I think the term context is too vague as well. Like context can be predicting the word after a previous word. You know, the man went, so trying to predict went. Whereas you could talk about context the way you were talking about earlier. You know, the previous paragraph, did the boy have a ball in the previous paragraph? And I think it's too vague. You need to be, if you're writing a paper, you need to be specific about what you mean when you say context. In my opinion.
Yeah, I agree.
Yeah.
I think in general, also this paper itself, they say, okay, we propose this kind of step, and then they go to the position-wise encoding, and then for the position encoding, they just add a new random stuff in there, which they half explain, half don't explain, and then your task as a reader is to puzzle everything together, right? And then you look at the papers they're referencing and so on. I say there is precedence, right? So if you look at some of the papers, especially papers that get cited a lot, they tend to be like a complete explanation of what they're doing, and you can have the paper by itself to understand. And these then also tend more people understand it, and people prefer to cite papers they understand. It feels like to me, except the rockstar papers who always get cited.
So I think here, by context, as you can see in the title, they just mean that there is some information earlier on that you, in normal transformer network you may miss. I think here that's what they mean. The term has been abused in the NLP literature. So usually it means attended over a sequence of states in your encoder. That's usually what it means.
But
if we go to the original.
you feed that information into the network will depend on the type of context you've learned, right? So if you fed it in a different way, so if you gave it 2-3 sentences at a time, it's going to learn something different than if you give it 2-3 words at a time, correct?
Yeah, that's fair.
So why does LSTM not performing well in that? I thought the long-term memory is designed to address the context issue. What's the intuitive reason why it's not working as good as you want?
Could you repeat the question? I'm trying.
Why does LSTM not performing remembering the context
Right.
good enough?
Do you wanna take that? Or? I've been talking too much.
Even LSTM has also a lot of hyperparameters, right? And especially LSTM has a lot of what's the forget gate, input gate size, hidden size, yada yada yada. And each of these gates are a mattress, and each mattress has a number of parameters, and a number of parameters has kind of a capacity, how much information they can store. And here, I think the ground rule is, if you have no limitations in memory, computation, whatever, you can always make a huge LSTM and then go with it. And they just say, here, in this architecture, look what we got here, right? We are faster and can monitor longer dependencies better, right? For the same number of parameters, right? You say you have 1,000 parameters, and you can do 100 position. Here you have this network, you have 1,000 parameters, and you can do, how many positions did I say before? 100 positions, right?
A few hundred.
Then 100 positions, you have 1,000, you can do 100 positions, or you have 1,000, you can do 400 positions, right? You just get more bang for your buck, right?
And to add to that, in general, RNNs are very difficult to train, right? You have that sequential piece that you can't really run in parallel, and they often face vanishing gradient problems. And also, I think what Florian mentioned, with attention, the whole point is that you can propagate information over arbitrarily long distances very quickly. Whereas in RNN, it's one step at a time, so what you're encoding is very vague from the past, and the information coming from the most recent steps is actually much more dominant.
Because it's hard to keep the information that's happened like
Yeah.
very much long ago. That kind of speaks to the point that you raised earlier. So like with attention, you get that hierarchical. And language is hierarchical in nature. Long distance dependencies do relate to each other a lot of times. That's why when linguists show them, they use parse trees. So that you have a much better chance to encode hierarchical information using attention and self-attention than a sequential encoding with such as LSTM.
Well, I just want to address that question from a different perspective. I would like to use Florian's, glossary example. If you're reading a paper and the glossary is on page 1, and you're reading page 10, you suddenly encounter an acronym. You don't try to memorize it. You just turn to page 1. Does that make sense? Okay.
I'm saying that LSTM is supposed to know, hey, this is a glossary, so it will stick into my long term forever. It's supposed to learn that.
Yeah, but
In reality,
if human doesn't attempt to learn it because it's kind of too niche. So yeah, why bother?
Yeah, it's all about learning efficiently the information, right? You'll have to memorize every word, so then the memory in LSTM would be huge, right? So then, even what's the point of the LSTM? Just use a fully connected neural network on everything. Yeah. It's all about the efficiency of information propagation on the network.
Why not use an attention model for the whole sequence? This is what they mentioned in the paper at the very beginning in the sentence, like, oh, if you can, you would just use an attention network over the whole sequence, over the whole document, right? And then you just read all hundreds of thousands of documents. But it's not feasible, right, computationally. And I think what Tara mentioned, is actually also more important with the vanishing and exploding gradient. And how do you do the evaluation with step-by-step in the trade?
So I think we'll get ready to wind down. Any last thoughts or questions before we end?
Okay, actually, Tara kind of brought it up, and this is kind of a hypothesis that I'm not quite sure. Basically, it works like this. For the position encoding, you know that each word has some kind of effective span. For example, the glossary has glossary and the acronym has much longer span. Yeah, and the abstract has much shorter span. You don't know these spans in the first place, so you assume that they're all kind of function. And the purpose of position encoding is to use a Fourier transform. Basically, learning the spectrum of each of those those effective span for each word. And because most of them are low frequency, so you're able to capture, you are able to, you're able to compress this kind of information in relatively few parameters. First, I'd like to ask, do you think it kind of makes sense?
I mean, theoretically, I think you're referring back to the paper also that you presented. It was a very good use of the
Fourier transform.
Fourier transforms and other spaces than more discrete space.
Yeah.
Theoretically, yes, but in practice, we need to see it. I think so. There is a lot of work that are trying to encode sequence into periodic sort of representation using Fourier transform, but entire like language model I haven't seen yet. But I think that's interesting to think about.
Okay, that back to the second question. If this is, well, if it kind of makes sense, then theoretically there shouldn't be significant performance between absolute position encoding and the relative position encoding.
So what was?
How do you do absolute position encoding?
Well, you start from you always start from the beginning of the article and assume that it is phase 0.
So you just put a number 0, 1, 2, 3 into the encoding?
No, that means you assume the beginning of every waveform that you use. The every wave in that matrix that is multiplied with the output of the attention output. It always starts from 0 at the beginning of the article. Wherefore, if it's the relative position encoding, then it is always 0 at the place where all the contextual information are aggregated into the last layer.
Okay.
I